let's apply the method of maximum likelihood to fitting a couple of distributions. The first distribution that we're going to fit is a normal distribution. Okay, let's assume here that we have some repair time observations. Okay, let's say we have a process or a system, some kind of machine or something like that, that breaks, and then we repair it, and we want to observe the amount of time that it takes to repair that machine. And let's say we observe the repair time 50 different times. We have 50 different observations of repair time. And let's assume that that repair time follows a normal probability distribution. Okay, we'll test this assumption later, but let's just assume for now that it follows a normal probability distribution. And so what we want to do is find what are the optimal values of mu and sigma that give us the best normal distribution for these 50 observations. Okay, that's essentially what we're doing with the method of maximum likelihood. We want to optimize, we want to maximize the likelihood that these observations came from a normal distribution with particular values of mu and sigma. Okay, so to do that, let's first evaluate the PDF for each one of our realizations, each one of our observations of repair time. Okay, so we need to implement this function right here. This is the PDF. We didn't use this a great deal in class because we had the standard normal function, the standard normal tables to convert a particular value of y over to the standard normal distribution and look up values of probabilities. But this would be the PDF that we would use in the method of maximum likelihood. Okay, to operate Excel, the Excel solver, we need initial guesses as to what mu and sigma, these two parameters, might be. Okay, for us to even evaluate this function at y equals 278.2, we have to have at least some kind of initial guess for these things. Okay, so mu is the overall mean of observations. We can just kind of come up with a guesstimate of what mu might be. Let's just throw out the number 300. Okay, mu for these observations is probably going to be somewhere in the vicinity of 300, maybe a little more, maybe a little less, but that's at least a good start. And then the standard deviation here, let's just assume it's 50. Okay, by looking at these observations, we might be able to assume that sigma would be a good starting point. 50 would be a good starting point for sigma. So now let's evaluate these observations. Okay, so we're going to implement this function over here. So that's 1 divided by sigma times the square root of 2 times pi. Okay, there's a built-in pi function in Excel, pi, and then parens. And then we'll close these things up. Okay, so this is, and I always get happy with these parentheses. So this is the first part right here. Now we're going to multiply that by the exponential function. That's going to be negative 0.5, negative 1/2, times, we've got y, our first observation here, minus mu, divided by sigma. Okay, and we need to square the y minus mu divided by sigma, and close out the exponent. Okay, so this is our first, this is our guess, our initial guess as to what the PDF would be evaluated at 278.2, what that evaluation would look like. Okay, what would this function look like evaluated at y equals 278.2, assuming that mu is 300 and sigma is 50. Okay, and what we want to do here is not retype that equation over and over and over again. We just want to drag this down for all 50 observations. But whenever we drag that down, our mu and sigma are going to change. Those cells are going to drag down with it unless we hold them constant. So we need to hold these values constant, okay, by putting dollar signs in front of the row and the column. Really, since we're just going to be dragging this down straight, we could put dollar signs just in front of the two rows, row 1 and row 2. However, let's just hold the entire cell constant. It's not going to hurt us either way. Okay, so we're going to put dollar signs in front of the column G and the row 2 to hold this sigma value constant. And we do that for all of the times that G1 and G2 show up. For B2, we want to let that roam free. Okay, whenever we drag this down, we want that to be able to change, because that would change with our observations. But we want to hold those mu and sigma constant. Okay, so whenever we drag this down here, we've got all of these values. We've got all the PDF evaluations at our different repair time realizations. Okay. Note here, for example, B6, our function dragged down B2 down to B6 whenever we drug the cell down. Okay. So now what we could do here is evaluate our likelihood function as the product of all of these. Okay. What does the product of all of these look like? It's going to be a very, very small number. Keep in mind, we're multiplying together 7 thousandths by 6 thousandths by 6 thousandths and so on. These are all very small numbers, and whenever you multiply 50 very small numbers together, you get something that's really small, 1 times 10 to the negative 122. Okay? That may not be very efficient to try to perform optimization on a number like that. So what we can do here is go ahead and apply the natural log to each one of these and then sum them up. Okay? The reason that we applied the natural log in the analytical solution that we talked about in the Lightboard video is because whenever we perform calculus on the natural log of the likelihood function, we are performing calculus on, or taking a derivative of each one of several functions added up. If you multiply those up, it gets difficult. If you can add them up, it gets easy. Well, that also works here because we're going to be dealing with a likelihood function that's not going to be nearly as small as 1 times 10 to the negative 122. Okay? So we're going to take the natural log of each one of those, and then we're going to add those up. Okay, so our natural log likelihood function is just the sum of all of these values. Okay, so this is our natural log likelihood function when we assume that mu is 300 and that sigma is 50, when we assume a normal distribution for these 50 observations. So now this is the value that we want to maximize. We want to maximize the natural log likelihood by changing these cells. Okay, we want to find where are the best values of mu and sigma that maximize this function. To do that, we need the solver. So we go to the data tab and we go over to the solver function. Okay, to add this in, I've already added it in on this computer, but to add this in, you go over to, obviously I'm using a Windows machine here. We go over to options, go into add-ins, and one of the Excel add-ins, if we were to go to that, is the solver add-in. Okay. So now let's use the solver. Okay. You can read up more about the solver. I'm just going to use this in a very rudimentary way. There's plenty of options that we could look at here. And then there's a lot of stuff going on behind the scenes that you should be a lot more familiar with. We're just going to touch on this very basic idea. And that is to set an objective, which is this function right here, that cell. We want to maximize that by changing these two cells. Okay, we want to maximize the natural log likelihood function, which is found here, by changing the values of mu and sigma, which are found here. Okay, and we're going to do that with an evolutionary algorithm. Okay, this is just a heuristic algorithm. This does not provide us an analytical solution. We're not going to find the exact optimal values of mu and sigma, but we're going to approximate them. So essentially what heuristic algorithms do is, again, without using calculus, they search for a ton of different values of these mu and sigma here, and they record the maximum, they record the mu and sigma that give the maximum value of the natural log likelihood function, and then they just keep searching over and over again until they can beat the maximum that they found so far. Okay, that's a quick and dirty explanation of what heuristic methods do. Okay, and one such heuristic method is called an evolutionary algorithm. Okay, and that's the one we're going to implement here. To implement this algorithm, we have to have upper bounds and lower bounds for these two cells. Okay, so essentially we have to impose a reduction in the search space. In other words, we don't want the computer to just search every single possible value from negative 3 million to positive 850 billion. Okay, we don't want to search that much. Okay, let's try to narrow down the amount of work that the Excel solver has to do with this evolutionary algorithm. Okay, so let's realistically add some bounds. So let's add a lower bound for mu. Okay, and let's say that the lower bound is not going to get any smaller than, let's say, 200. I mean, the mean of these observations is not going to be any smaller than 200 for sure. In fact, it's probably not going to be any smaller than 250, but let's just leave it at 200. Okay, and let's add an upper bound. Okay, so mu must be less than or equal to, let's say an upper bound here is going to be 400. Okay, the mean of these observations is not going to be bigger than 400. Okay, now let's set a lower bound. Okay, sigma must be greater than, let's just throw a number out there, 20. And the standard deviation for these observations is probably going to be smaller than, let's say, 100. Oops. Over here. Okay. So now we've got upper and lower bounds for each one of our decision variables, the values that we're solving for. We're going to use the evolutionary algorithm. There are some other options in here which you might want to take a look at, okay, just depending on what you need. Let's start running this solver. Okay, so the solver is running several observations, and it's, you know, we can sit around here and wait until the solver is completely finished. Okay, that is, that it's reached some level of error that it's okay with, that it hasn't improved the optimal value that it's found so far by very much, or we could set with the options in the Excel solver, we could set an artificial number of a search length or something like that. Or we can just use escape after a while and say, yeah, that's good enough. And let's say that it's good enough. We could continue or we could just stop. Let's just stop, save our solutions. And what this says is, based on however long we just ran the evolutionary algorithm, the optimal value, the approximately optimal value of mu is 345.5 and sigma is 43.2. Okay? And then I ran this previously, and so those were the numbers that I got previously. So what we're saying here is the maximum likelihood estimates for a normal distribution to fit these 50 repair time observations are 345.5 for mu, 43.2 for sigma. Those are the two values of the two parameters of this distribution that maximize the natural log likelihood function. Okay, we didn't have to use calculus. We used, in this case, a heuristic algorithm that's built into Excel. There are better algorithms. Okay, we didn't need anything really hardcore to solve this. There are better algorithms to use. There are other more sophisticated software packages to use. But Excel is pretty ubiquitous. A lot of people know how to use it. And this is a pretty straightforward kind of implementation. So if you have some observations, you could fit a probability distribution. Is this the best probability distribution to fit? Do we know that these observations are normally distributed? We don't know yet. Okay, we'll run a goodness of fit test to see. But if the best distribution for these 50 observations is a normal distribution, then these are the two best parameters to be using.